Have you ever stood in a room trying to figure out how much paint to buy and then realizing you also need to figure out how much baseboard trim you need? Well, they're two totally different measurements. In this explainer, we're going to unlock the simple secrets behind measuring shapes, making all that confusing geometry stuff actually make sense.
Okay, let's just jump right in with a real-world puzzle. You're redecorating. You need carpet to cover the entire floor, and you need baseboard trim to go all the way around the edges of the room. So which measurement is for the carpet and which one is for the trim?
If you said perimeter for the baseboard and area for the carpet, you absolutely nailed it. And here's a super simple way to remember that forever. Just think of a yard. The perimeter is the fence you build around the lawn. It's just a length. The area is the actual lawn itself, all the green space inside that fence. One is a line, the other is a surface.
So now that we've got the fence and the lawn straight, let's focus on the lawn for a bit, the area. How do we actually measure all that space? Well, it all starts with one single, perfect little building block.
And here it is, the humble square centimeter. You know, you can think of it as our little Lego block for measuring space. The area of any shape, it doesn't matter how weird it looks, is really just the answer to one simple question. How many of these little squares would it take to cover the whole thing? It really just comes down to counting squares.
And that's the key, the famous formula we all had to memorize. Area equals length times width. It's not just some random rule. It's actually just a super fast shortcut for counting all those little square tiles inside a rectangle without having to count them one by one.
Okay, so rectangles are pretty straightforward. But what about all the other shapes out there? Well, this is where it gets really cool, because a lot of the most common shapes are actually just rectangles in disguise. You just have to know the trick to unmask them. So take a look at this parallelogram. It's basically a rectangle that just got kind of lazy and decided to lean over. Now, your first instinct when you want to find its area might be to measure that slanted side, right? But that is a classic trap. And here is where the magic happens. Watch this. If we just slice off that little triangle from one end and then slide it perfectly over to the other side, boom, we've made a perfect rectangle. We haven't changed the amount of space it takes up at all, so the area is exactly the same.
And that is why the idea of height is so important. The height isn't that slanted side, it's the straight up and down distance from the bottom to the top. Why does that matter? Because that straight line is the exact side of that hidden rectangle we just uncovered.
So when you look at the formulas side by side, it all just clicks. For a rectangle, we use its base and its height. And for a parallelogram, well, it's also base times height. Turns out they're the same idea. One of them was just wearing a really clever disguise.
All right, so we've seen how to rearrange shapes. Now let's see what happens when we start slicing them up to understand them even better.
And here's another one of those simple but really powerful secrets. You can take any parallelogram and slice it diagonally right in half, and you'll always get two identical triangles. They're perfect mirror images. And that discovery leads us right to the formula for a triangle. I mean, since we already know the area of the whole parallelogram is just its base times its height, it makes perfect sense that the area of one of those triangles has to be exactly half of that. Base times height divided by 2. And just like that, you understand why the formula is what it is. It's not just a random rule, it's just half of a parallelogram. All right, next up, the rhombus. It kind of looks like a tilted square, but its secret isn't about sliding pieces around. This one is all about the lines that cross right through its center, what we call the diagonals. So check out this brilliant visual trick. If you draw a rectangle perfectly around the rhombus, so the edges of the box just touch the points of the rhombus, look what happens. You create 4 new little triangles in the corners. And the really cool part is, those 4 triangles on the outside are a perfect match for the 4 triangles on the inside. What does that mean? It means the rhombus takes up exactly half the space of the rectangle around it.
And this just proves why the formula works. We're just finding the area of that bigger rectangle by multiplying the diagonals together, and then we chop it in half because we know the rhombus only fills half that space. Simple.
Okay, so we've learned some really clever tricks for finding the area, the lawn. Now let's switch back to the fence, the perimeter. We're going to look at a shape that seems incredibly complicated at first, but with one simple trick, it becomes an absolute piece of cake.
So how in the world would you find the perimeter of a shape like this?
Your first reaction is probably just a groan, right? I mean, you think you have to measure every single one of these little jagged edges and then add them all up? What a nightmare. But watch this fantastic little trick. We can take all of those little vertical lines on the inside and just slide them all out to the right. Then we take all the horizontal lines and slide them up to the top. The total length we're measuring hasn't changed one bit, but we've just turned that jagged mess into a simple, clean rectangle. And here's the punchline. The perimeter of that super complicated, jagged shape is the exact same as the perimeter of the simple 8 by 6 centimeter rectangle it makes. So we just do some easy math. 8 plus 6 is 14, times 2 gives us 28 centimeters. We didn't have to measure all those little tiny pieces at all.
So, what are the big ideas to take away from all this? First, always remember the fence and the lawn to keep perimeter and area straight in your head. Second, remember that most of these area formulas just come from the idea of a rearranged or sliced up rectangle. And finally, don't ever get scared by a complex looking shape. There's almost always a clever way to simplify it. So, we've pretty much mastered 2D space, the fence and the lawn. But what happens when we take these flat shapes and give them a third dimension and start building the house itself? How do we measure the space inside that? Its volume? Well, that's the next dimension to explore. Thanks for joining this explainer.